5 documents. A knowledge base holding millions. And the model believes the 5. Your vector database is doing its job perfectly here, which is exactly the problem, and almost nobody is defending against it. Researchers dropped 5 malicious texts into a knowledge base of millions of documents, and the system parroted the attacker's answer about 90% of the time. Best case, 97. 5 documents, against millions. And it works no matter which vector database you picked. Mental model first, because the mechanism only lands afterward. You built a library and you trust it. The attacker never broke in, never touched the catalog. They edited one book on one shelf, slid it back, and waited for a librarian to read it aloud to somebody who trusted the librarian. So how does it break? In your architecture diagram, retrieved chunks look like reference material, data you hand the model to read. That is not what arrives. We have seen this disease before. SQL injection was the same confusion, data and code sharing one channel. And we fixed it properly, with a structural boundary rather than a blacklist of quotes and the word drop. The query shape compiles first. The value arrives separately, and it can never become syntax. So do the same for prompts. You can't. There is no prepared statement for a language model. The SQL boundary worked because it was syntactic, and a parser could separate code from string at compile time. Prompt injection is semantic. The payload arrives as a perfectly well-formed English sentence, and no parser on earth can reject it. Watch the pipeline. Documents get ingested, chunked, embedded, written to a vector store. A question comes in, gets embedded, the nearest chunks come back and get pasted into a prompt. That dashed line at the top is the part that matters. Most corpora re-index on a schedule. A page edited today is in your index tomorrow, and nobody read it. Split the problem in 2 before we go further, because these are separate attacks with separate defenses. You can poison the corpus, planting text the model reads as a command. Or you can poison the embedding, engineering which chunk gets retrieved at all. Almost every talk you have sat through covers the first one. So, surface 1. Ask who can write into your corpus. The honest answer runs wider than the one you would give in a meeting. Every one of these is an ingestion path. GIT Lab learned it the hard way. Issue titles went straight into their AI assistant, so a ticket filed by a stranger became model input. And the payload can look like nothing at all. Your reviewer opens the page and sees a normal refund policy. The chunker sees every character. White on white paragraphs. 0 with spaces splitting keywords apart. All text and HTML comments. Eyeballs are not review, which is why we ship a scanner in this repo. This is the study to know. Usenic Security, 2025. 5 malicious texts per target question dropped into a base of millions. 97% on natural questions, 99 on Hotpot QA, and MS Marco came in at 91. All black box, so no access to the model or the index. The authors ran the existing defenses themselves and reported them insufficient. So why is it that cheap? Do the arithmetic nobody does. Your retriever never hands the model the corpus. It hands over the top K results, and K is usually about 5. The attacker isn't fighting millions of documents for attention. They need to outrank for other chunks. That is the whole contest. Sit with that, because it inverts what everyone assumes. The instinct says a bigger knowledge base dilutes bad data, more good documents, less chance the poison surfaces. Wrong. The retrieval window is the same size whether you hold 100,000 chunks or 100 million. Same 5 slots, every single query. And it got cheaper. A follow-up called CorruptRAG, April 2025, cut it to a single poison text per question and still cleared 90%. That matters for detection as much as for cost. 5 injected documents is a volume anomaly you might plausibly catch in review. 1 edited page is a Tuesday. It survived paraphrasing, it survived instruction-based prevention, and it survived having a second model screen the retrieved text. Surface 2 is where retrieval becomes its own security problem. Forget planting text. Think about the embedding. Queries about a topic land in one region of vector space. Optimize a passage so its embedding sits in the middle of that region and it never has to be relevant to any particular question, because it sits close to all of them. This is not a thought experiment. Gaslight, presented at ACM/CCS 2025, does exactly that with gradient search. Injecting 1/10,000% of a corpus put the attacker's passage in the top 10 results for between 61 and 100% of queries the attack had never seen. No corpus access, no changes to the model, and they demonstrated it against a real deployed RAG application. And this deserves its own conversation. Prompt injection is about controlling what the model does once it has the text. This is about controlling which text it gets. Different layer, different failure. Your prompt injection guardrail also sits downstream of the retriever, so by the time it looks at anything, the choice was already made. So what does a successful attack do? 3 outcomes. The first one is quiet, and the most likely. The model states something false, wrapped in your company's authority, to an employee who has no reason to doubt it. Nothing crashes, no alert fires, and nobody files a ticket. The system did exactly what you built it to do. The second outcome is exfiltration, and the mechanism is almost insulting. The injected text asks the model to summarize something sensitive, then render an image whose URL carries that summary. No exploit code. It's a markdown image. The victim's own client fetches it, and the data walks out through the interface, nowhere near whatever your egress monitoring is watching. And this one shipped. EchoLeak, disclosed June 2025 against Microsoft 365 Copilot. CVSS 9.3, 0-click. The user only had to ask Copilot to summarize their inbox. The attack walked past Microsoft's own injection classifier, used reference-style markdown to dodge link redaction, and pulled the data out through an auto-fetched image. The third outcome is where this stops being a chatbot problem. In agentic RAG, the retrieved text reaches something that acts. A tool. An API. A shell. Simon Willison has the cleanest frame for when this turns critical, and he calls it the lethal trifecta. Access to private data. Exposure to untrusted content. Some way to send data outward. Hold any two and you are broadly fine. Hold all three in one session, and a poison chunk has a complete read and exfiltrate path without a single line of exploit code. 2 failures that almost never make it into a threat model. First, people treat embeddings as a one-way transform, derive data rather than the real thing. They are the real thing. Inversion research recovers the source text from the vector alone, over 90% accuracy on short passages, including full names pulled straight out of clinical notes. Training the inverter takes text and embedding pairs. No model waits. Second, permissions get checked at the wrong time. Most teams copy a document's access list into the vector metadata when they index it. That is a snapshot. Someone changes teams, loses access to the source folder, and the source system honors that instantly. Your index doesn't. The vector still carries the permissions it had the day it was written. And this has an official name now, which helps when you are justifying the work to somebody holding a budget. OWASP added vector and embedding weaknesses to the top 10 for large language model applications. Its for subclasses map almost exactly onto what we just walked through. Stale access controls, cross-tenant leakage, corpus poisoning, embedding inversion. So what do we do? Rule out the reflex first, which is to sanitize the input. It cannot work here, and the reason deserves precision. SQL has a grammar. A quote is a token, and the parser decides. Here, there is no grammar. The capital of France is Berlin is a perfect semantic match for a question about France. Nothing at retrieval time can flag it. Then the guardrail classifier, which is a pattern matcher dropped into an adversarial setting, and those lose over time. The sharper issue is that pure factual corruption has no instruction shape to detect. Nothing imperative in it. Nothing to flag. And we have the receipts. EchoLeak walked through Microsoft's classifier, and Corrupt RAG survived screening by another model. Reading what the defense papers assume, each retrieved document stands on its own. That several relevant documents exist to vote down the bad one. That the retriever was accurate, which is the exact thing under attack. Oh, and spare compute to cross-check every query. Real corpora break all four. I do not want to leave you scared, so read that 97% carefully. It is one dataset's attack success rate on an attacker-chosen question in a benchmark corpus. It says nothing about how many production systems are compromised. Poisoning is cheap. It isn't free. The poison still has to get retrieved, and large, private, frequently re-indexed corpora are genuinely harder targets. So what actually helps? 3 things, and all of them are architecture rather than filtering. First, provenance. Every chunk arrives looking identical right now. A memo your CTO wrote and a PDF you scraped off a vendor site are indistinguishable by the time they hit the prompt. Stamp a trust tier at ingest, carry it into the context, and put it in front of the human. Second, move the authorization check. Same diagram as before, one thing moved. Stop copying permissions into the index at write time. Store the vector, and evaluate live authorization at query time, against the source system, on every single request. Then revocation works the way everyone already assumes it works, because no snapshot is left to go stale. It costs you a lookup per query. That is the whole price. Third, go back to the trifecta and cut one leg. That is the game. An egress allow list, so the client cannot fetch arbitrary URLs. No auto-rendering of images or links out of model output. Privilege separation, so the component reading untrusted content isn't the one holding the credentials. Every serious control is one of those 3 cuts. None of this means stop building RAG. It means know which one you built. If outsiders can write into your corpus, if your agent holds tools, if one index serves many tenants, or if your client auto-renders whatever the model emits, you are in the top row. A curated, read-only corpus behind a single tenant with no outbound channel is a genuinely different risk. There is no known complete fix for prompt injection, and anyone selling you one is selling you a filter. What you can control is reach, meaning what a poison chunk is able to touch once it wins the retrieval race. So go measure the blast radius of your own top 5, and count how many of the 3 legs your system is holding right now. If clear, sensible thinking is what you are after, subscribing is the most direct way to get the next one. See you in the next video.